Let's now move to the question number 43. The total electric flux from a cubical box. Okay, they gave us the length of one side of that box. So we have a cubical box. It's like a cube. You see, it's like a cube. Okay. So we have this cube here. Okay. One side of that is just 28 centimeter. Okay. The total electric flux on a side is, a side means on one face of it, okay? Just 1.45 10 to the power 3 Newton meter square divided by Coulomb. What charge is enclosed by the box? So they are looking for the Q enclosed inside the box, okay? To find that, actually, you know the story. Now we are looking for, now we have been given not the electric field, but we have been given the electric flux. Don't forget this. Flux is this sign here, phi, okay? And we know there is a relation actually between phi and the charge enclosed, okay? We know that phi equals to the, okay, the integral of the electric field multiplied with the Gaussian surface, and that should equal to the Q enclosed with that Gaussian surface over the free space of permittivity, epsilon naught in this case, okay? So we are not looking for E or the area, so we'll just put the electric flux in this short form equals to Q enclosed, this is the Q enclosed here, divided by epsilon. And from here we can get Q enclosed easy, okay? Because now we have been given the electric flux, which is this one, and we should look for the units. Everything is fine, yeah, meter, Newton, Coulomb, so that's fine. And then we know that this is constant, then we get the result directly. That means no need sometimes to put electric field and find the Gaussian surface. We just simply use the equation as simple as it is, okay? Because we have been given the electric flux and the constant, which is the free space permittivity. Okay, but the question already gave you this amount here, which is the one side of the cube, okay? Do we need it? Do we have to plug it inside the equations? No need, actually. Sometimes you don't need extra information. So that is just extra information for you in this case, okay? But you should also take aware of about the vocabulary here. Sometimes they are all words or phrases, because sometimes they are saying it is a positive or negative electric flux. So you should take care about that one. Okay, let's now move for the last question here, which is 49, okay? A solid metal sphere of radius 3 meter. So we have a solid metal sphere, okay? Okay, let's choose another color. Okay, so this is a solid metal sphere with a radius is 3 meter. Okay. Carries, so look, it's a metal. A metal sphere means it's a conductive sphere. Carries a total of charge of, okay, minus 3.5 microcoulombs. What is the magnitude of the electric field at a distance from the sphere's center of A, B, C, D? Okay, and then how would the answer differ if the sphere were a thin shell? Actually, this thin shell will take it, inshallah, in the coming lecture, okay? Don't worry about that. So let's take the first part. Okay, so now we have a solid sphere. So this is a solid sphere, okay? We know the radius, it's given, and they are giving us different numbers for different locations with different distance from the center. First of all, what is the radius? This is very important. What is the radius of the solid metal sphere? It is 3 here. 3 meter. Okay, so if it's 3 meter, we should ask ourselves, what are the distance that we should find the magnitude of the electric field? Okay, what are the magnitude? Sorry, what are the distances? A, 0.15. Oh, 0.15 is less than this. So they are asking us to find it inside here. Okay. B, 2.9 meter. 2.9 meter is also less than 3 meter. It's also inside here. We're still inside. Okay. C, oh, C now outside. We are now 3.1. 3.1 is larger than 3. So we are here outside. This is for C. D, 6 centimeters. So this is D. But A, B are inside. Okay, again. So now we have 4 Gaussian surfaces. Okay. Why we make Gaussian surfaces? Because we said that all points on the Gaussian surface for a spherical Gaussian surface is a good choice, because it make a symmetrical condition that can be equalize all the electric field only in that surface, the Gaussian surface. Okay. A and B are inside the metal surface. Okay. So if anything inside metal surface, and any surface, any point, not any surface. If this is a metal surface, so metal in red, okay, and we choose this point here, any point here inside here, any point inside. Always we said that electric field inside is 0. Excellent. So electric field inside is 0. Okay. Why is 0? Because there is no Q enclosed, as we said, because we know that is phi equals to the integral, closed integral of, yes, E into delta A. Okay. And this should equals to Q enclosed divided by epsilon naught. Okay, there is no Q enclosed here. Q enclosed 0, so E is 0 in this case. Okay, so there is no electric field. So in A there is no electric field. You can see here E is 0. So always inside a solid metal sphere, the electric field is 0. Don't forget, this is a conducting, okay, sphere. It's a conductor, like iron sphere, like a sphere made of copper, whatever. Again, for B, we're still inside. B is 2.9 and the radius is 3, so we're still inside. Again, at B, the electric field is 0. Okay, what about outside, which is the case of C and D? Okay, we have the law and the relation. The relation is this one. We got it actually last time, yes? So we know from previous that electric field equals to Q over R square. And this is actually like a point charge. We said last time, if this is actually a conducting material, a sphere, then outside here, as if it's like a point charge, and we are looking for the electric field outside, the same thing. So the electric field, we treat that metal sphere like a point charge, so then the electric field will be the same equation. Okay, we know this is constant. Q, it has been given, and the distance at C, it is 3.10 meter. It's not a centimeter, it's a meter. Okay, so this will be the result, and don't forget the units here. Okay, what about D? The D is the same thing, but we change only the distance. Instead of 3, 6, and it should be lower. You see, this is 8.74, 10 to the power 2, but here 10 to the power 3. Okay, as we go far away from the metal sphere, the electric field is decaying. But if we are, so this is the R, capital R, and this is the R small far away, okay, and this is the intensity of the electric field. Okay, so electric field here is 0. Let's choose another color. So here is 0 until we reach actually the maximum radius of that sphere, and from here you can see this is the maximum here at R. Then you can see that start to decay because the relation between E with the reciprocal of R squared, okay? That is the relation, okay? Okay. E, there is no difference. We will see, inshallah, within, the thin metal shell. What is this metal shell? It's actually like this shell here, okay? So it is a shell, okay, vacuumed from here inside, but it has this kind of thickness, and we'll discuss it later on. We can understand that very well, okay? So we finish with the questions, and thank you very much.